Hello. So today what we're going to be talking about is increasing and decreasing functions. Now the further we get into calculus, um, we're going to learn more and more ways to analyze functions using different calculus methods. So the only real thing in calculus we've learned so far is about the derivative, and mainly that first derivative. So we're going to learn a new way of using the first derivative to analyze a function. So first, what are some definitions for increasing and decreasing functions? We say that a function is increasing on an interval if for any two numbers a and b inside of the interval, if a is less than b, then f of a is less than b. So in other words, when you have two x values and one of them is less than the other, if the function is increasing, the y value for that x value that's smaller should be smaller than the other y value. And then it's just the opposite for decreasing functions. A function is decreasing if you have any two x values in an interval and you know that a is less than b, if the y value for the first x value is larger than the y value for the second, it's a decreasing function. So that's a lot of words and a lot of symbols. So what does that really mean? So say we have an interval here from a to b. And we're going to be talking about increasing functions here. So we know an increasing function should be getting larger from the word increasing. So that just means that if we have an increasing function, f of a should be less than f of b whenever a is less than b. So maybe our function looks like that. And it's the opposite when we have a decreasing function. So if we have a decreasing function, then the y value at the start of the interval should be larger than the y value at the end. So in other words, f of a should be larger than f of b. So maybe our function looks something like that. Those are two examples of increasing and decreasing functions. And the definitions should hopefully match what you intuitively think about the words increasing and decreasing. So increasing, y values are getting larger as you go further into an interval. Decreasing, they're getting smaller. Okay, so now we have this other theorem, which is going to talk to us about how we actually go about finding them. So if we have a continuous function that's also differentiable on an interval, if the derivative is positive for all of the x inside of that interval, then x is increasing. So in other words, positive derivative, so positive f prime of x equals increasing function. So hopefully you're thinking the opposite is true then. If we have a negative derivative, so if we have negative f prime of x, then we know that we're decreasing. And then in the third case that could happen, you could have that your derivative is not less than or bigger than 0, it's actually equal to 0. So if f prime of x equals 0, then it's a constant function on that interval. So that means the y values aren't changing. So in other words, if we have positive tangent lines, positive derivatives, we have an increasing function on the interval. And if we have negative tangent line slopes or negative derivative values, then we know that we have a decreasing function. But if we have that the derivative is equal to 0, then we know that it's constant over that interval, or it is at least constant at that one point. So let's do an example problem. Let's find the open intervals where f of x is increasing and decreasing. Well, the last theorem told us that if we want to find where f of x is increasing or decreasing, we need to look at the derivative. So as a reminder, it's increasing when f prime of x is greater than 0 and decreasing when f prime of x is less than 0. So in order to find where f prime is bigger and smaller than 0, we should probably find f prime of x. So f prime of x is just the derivative of f of x, and that's pretty easy to do since we have a nice polynomial function there. So derivative of x cubed is going to be 3x squared minus 3 halves times the derivative of x squared, which is 2x. Now we'll just clean it up a little bit and get 3x squared minus 3x. Okay, so now the first thing that you want to do when you're finding the intervals where f of x is increasing and decreasing is you want to look at where the derivative is equal to 0. You want to find those critical values. So you want to look for where f of x either equals 0, so our critical values come from, or our critical numbers they're sometimes called, come from where f prime equals 0 or f prime is undefined. Now since we have a nice polynomial derivative, we don't have to worry about the f prime being undefined case, so we'll just cross that off. So we want to set the derivative equal to 0 and solve for those x values, those critical values, because they give us places to start looking for those increasing and decreasing intervals. So solving this, let's factor a 3x out of each of the terms, because that's our greatest common factor. So we're going to get 3x times x minus 1. Splitting it up, we're going to get 0 is equal to 3x, and 0 is equal to x minus 1. So 0 is equal to x, and 1 is equal to x. So now those give us some test values to look around. So we know that something is happening with our function at x equaling 0 and x equaling 1. So what we're going to do is set up something called a sign chart, where the top is going to be f prime of x, and the bottom is going to be where our x values are. So we know that our critical values were at 0 and 1, and we know that that's where the derivative is equal to 0. So I like to put zeros above them to remind myself that that's where the derivative is equal to 0, because sometimes you get critical values where it's undefined, so you want to differentiate for yourself which ones had 0 derivatives and which ones had undefined derivatives. So now we know that the derivative is 0 at those 2 points, but what's going on in between them and around them? So in other words, we want to pick test values that are going to be in all of the intervals that those 2 critical values split the x-axis up into. So why don't we pick some test values? So let's pick one to the left of 0, negative 1 might be a good choice. One in between, so maybe 1/2, and then to the right of 1 or 2. You always want to try and pick easy numbers to plug in. If 0 is not a critical value, you might want to pick 0 to plug in just because it's always the easiest number to plug in as long as it doesn't make your function undefined. So now let's plug negative 1, 1/2, and 2 into our derivative and see what happens. So let's find out first what f prime of negative 1 is. So f prime of negative 1 is going to be equal to 3 times negative 1 squared minus 3 times negative 1, which is just equal to 3 plus 3, or 6. So it's positive there, so we're going to put a positive sign over the negative 1. You could write the number, but sometimes having a lot of numbers up there can be a little confusing, and we don't want to confuse ourselves. So now let's find f prime of 1/2, which is going to be 3 times 1/2 squared minus 3 times 1/2. That's just going to be equal to 3 times 1/4, or 3/4, minus 3 times 1/2, or 3/2. So now creating a common denominator, we're going to get 3 over 4 minus 6 over 4, which is negative 3/4. So our derivative is negative there, so let's put a negative sign over the 1/2. And then all we have left to do is find f prime of 2. So we'll do that work over here. So f prime of 2 is just 3 times 2 squared minus 3 times 2, which is 3 times 4 minus 6. So here we're going to get 12 minus 6, which is positive 6. So we're going to put a positive sign above the 2. So now all that's left to do is that we have to write our intervals, our answers down. So you always want to write your increasing and decreasing as intervals, because it's not just happening at a singular point, it's happening over the whole real number line. So looking at our sign chart here for the derivative in x, let's write down all the intervals for increasing first. So that's all of the intervals where we have a positive derivative. So we have 2 plus signs here. So we're going to have 2 intervals. So since the derivative is positive to the right of 0, it's positive for all of the numbers to the right of 0. So we want to write the interval that represents that. So all of the numbers to the right of 0 could be expressed as the interval from negative infinity to 0, then union that second interval. So there, it looks like all of the numbers from 1 out to positive infinity are going to have a positive derivative, because if it changed to a negative derivative, there would have had to have been another critical value. So now we can write union 1 to positive infinity. And then we're going to do the same thing for the negative interval for decreasing. So our function is decreasing here in the middle, and that looks like it's for all of the numbers in between our 2 critical values. So we're only going to have one interval here. We can write that as 0 to 1. And it's as simple as that. It's the same process for any other function. So to find intervals of increasing and decreasing, you're going to find your derivative, set it equal to 0, and solve for your critical values. So find when your derivative is equal to 0 or where it's undefined. You're going to set up that sign chart, that number line, plug in different test values around your critical values, find the signs of the derivatives, and then write your intervals at the end. Simple as that. So let's do another one. So let's find the open intervals where f of x is increasing and decreasing for this function. So again, our first step is going to be to find our derivative. So again, it's fairly easy for us since we've got a nice little polynomial here. So we're going to get f prime of x is equal to 3x squared plus 6 times the derivative of x squared, or 2x, plus 0 for the derivative of 15. So that's going to be 3x squared plus 12x. So now we want to find our critical values, or our critical numbers. So to do that, we have to look for if it's ever undefined. So since f prime is again a polynomial, we don't have to worry about it being undefined anywhere. So let's set it equal to 0 and solve for x. So 0 then is equal to 3x squared plus 12x. Now to solve this, again, we're going to want to factor out a common factor. So it looks like I can take a 3x away from both of them. When I do that, I'm going to be left with an x plus 4. Again, since it's set equal to 0, we can split it up into 0 equals 3x and 0 equals x plus 4, which gives us that 0 is equal to x and negative 4 is equal to x. So again, we're going to go ahead and set up that sign chart, find our test values, and then plug into our derivative. So I have critical values at 0 and 4. Remind myself that the derivative is 0 there. Okay, and so now let's pick some test values. So we need one to the left of negative 4, and between negative 4 and 0, and to the right of 0. So negative 5 seems like a good option. Maybe plug in negative 1, and maybe positive 1. So now let's go ahead and do the math, figure out what we got going on. So f prime negative 5 is equal to 3 times negative 5 squared plus 12 times negative 5. Negative 5 squared is positive 25. 3 times 25 is 75. So we're going to get 75 minus 60, which is positive 15. So again, I can put a positive sign up here. Maybe we'll label this to remind ourselves that the top row is for our derivative, bottom row is for our x values. So now let's do the same thing for negative 1. So f prime of negative 1. Okay, so that's going to be 3 times negative 1 squared plus 12 times negative 1. So here we're going to get 3 times positive 1, or 3, plus 12 times negative 1, or negative 12, which is going to be equal to negative 9. So it's decreasing in that interval. And then one more value, we're going to do f prime of positive 1, which is equal to 3 times 1 squared plus 12 times positive 1, which is going to be 3 plus 12, or 15. So we got positive derivatives over here. So the last step that we have to do is just read our intervals off of our sign chart. So again, it looks like we have two positive intervals. So we're going to have two intervals for our increasing. So it looks like we're increasing to the left of negative 4 and to the right of 0, all the way out to positive infinity. So those intervals can be written as negative infinity to negative 4, union 0 to positive infinity. And then we could write our decreasing interval. That's going to be the interval between negative 4 and 0. All of those numbers in there, since there are no more critical values there. So that's going to just be the interval from negative 4 to 0. And you want to be sure to write the open intervals and not putting brackets on them, because the function isn't decreasing at negative 4 because it's got a derivative at 0. It's not decreasing there because it doesn't have a negative derivative. So you don't want to put brackets on your intervals there because that's wrong. Okay, so one more example and then we'll be done. So let's find the open intervals for this function where it's increasing and decreasing. So again, first step, find your derivative. So here, we could multiply all of those binomials together and get a nice polynomial to take the derivative of, or we could use our product rule and not have to do all that work. So I vote that we do that, because mathematicians are lazy, and why do all the work when you don't have to? Okay, so our product rule says that we do the derivative of the first one times the second. So that means we're going to do the derivative of x plus 2 all squared. So doing that derivative, we're going to bring down the exponent, do 2, keep the base the same, reduce the power to 1, multiply it by the derivative of the inside, so the derivative of x is 1, and then all we have to do is tack on the second part of the function. So then we get an x minus 1, plus, then we're going to do the derivative of the second one times the first. So the derivative of x minus 1 is 1 times the first part of the function, which is x plus 2 squared. Okay, so now let's just clean it up. So this is going to be 2 times x plus 2 times x minus 1 plus x plus 2 squared. So now, since it's a polynomial again, we don't have to worry about it being undefined. So now we can set this equal to 0 and solve for our critical values. So now you might be thinking, do I have to FOIL all that together anyway to solve for 0? We could, but we don't have to, and it wouldn't take us that long because they're small binomials and there's no extra coefficients on the x's. But we actually have a common factor of those x plus 2 quantities. So I'm actually going to factor an x plus 2 away from both of them. I'm going to be left with 2 times x minus 1 plus, when I take 1 x plus 2 away from the second term here at the back, I'm just going to be left with 1 x plus 2. And now it's a lot easier for us to simplify. So I can split this up as being 0 is equal to x plus 2, and 0 is equal to everything inside the brackets, which I can distribute that to now, so I can get 2x minus 2 plus x plus 2. So over here, I'm going to get that 0, whoops, not 0. If I move that 2 over to the left-hand side, I'm going to get that x is equal to negative 2. Here, if I simplify all my like terms, my negative 2 and my positive 2 will go away. I'm going to get 0 is equal to 3x, or 0 is equal to x. So now let's just set up our sign chart, find our test intervals, find our test values rather, plug them into the derivative, and then write our intervals out. So we have critical values at negative 2 and 0. Label the top row as f prime, the bottom row as x, just to remind ourselves. So now let's find some test values. So why don't I plug in negative 3, negative 1, and 1. Just some nice easy numbers. Okay, so plugging them into f prime of x, I'm going to get f prime of negative 3 is going to be equal to 2 times negative 3 plus 2 times negative 3 minus 1 plus negative 3 plus 2 squared, which is going to be equal to 2 times negative 1 times negative 4 plus negative 3 plus positive 2 rather is going to be negative 1 squared. Simplifying, we're going to get 2 times positive 4, or 8, plus 1, which is 9. Okay, so we know we got positive derivatives going on here. So let's do the same thing for f prime of negative 1. So there we're going to get 2 times negative 1 plus 2 times negative 1 minus 1 plus negative 1 plus 2 squared, which is going to be equal to 2 times negative 1 times negative 2 plus negative 1 squared, which is going to be equal to 4 plus 1, or 5. So again, we have a positive derivative. So now let's see what happens when we plug in positive 1. Just doing that work down here, get f prime of 1 is going to be equal to 2 times 1 plus 2 times 1 minus 1 plus 1 plus 2 squared, which is going to be equal to 2 times 3 times 0 plus 3 squared. So this first term is going to all go to 0, and then 3 squared is 9, so again it's positive here. So we have no decreasing intervals because we didn't get any negative derivatives. So we only have to write increasing intervals. And now you might be saying, okay, it's positive derivatives in all three, I'm just going to write all real numbers. But we can't do that because we have 2 points where it's not positive. These points right here, it's not increasing at those 2 points, so we can't just write all real numbers for our solutions because that would be saying it's also increasing at -2 and 0. So we're going to have to write all 3 intervals, but they're all increasing intervals. So we're going to be able to write the interval from -infinity to -2, union -2 to 0, unions up again with 0 to +infinity. So there you go. So that was a slightly harder one where we had to use more complicated derivative rules, but it's the same process every single time. Okay, so thank you so much for watching. Have a great rest of your day.